So today we will start with linear algebra, linear transformation. This is chapter 3 of Dr. A.P. Singh sir book, Linear Transformations. So do you remember the definition of linear transformation?
Not ma'am.
Okay. Let V and W be two vector spaces over field F. Then T mapping from V to W is said to be a linear transformation if it satisfies the following two properties. First property is T V1 plus V2 is equals to T V1 plus T V2, and V1 and V2 are from the vector space V. Second property, T alpha V. So scalar will come outside alpha TV for all alpha belongs to field and V belongs to vector space. So any mapping T which satisfies these two properties, then it is known as linear transformation. For example, F belongs to C infinity A comma B. C infinity A comma B means it is continuously differentiable, infinitely times continuously differentiable on this interval AB, such that f double dash x minus 2f dash x plus fx is equals to 0. So this is a homogeneous differential equation. So this will be a linear transformation. F plus g dash is equals to f dash plus g dash. Means linear transformation is defined in the form of a derivative. Alpha f dash, this is equal to alpha f dash. So this is a linear transformation. Also, if I want to find the solution fx, d square minus 2d plus 1 fx is equals to 0. So what will be the solution for this? Auxiliary equation will be
Y equal to C1 plus C2x into e to power x.
roots will be 1 and 1 na? So fx will be c1 e to the power x plus c2 x e to the power x. So dimension of w. So dimension of w will be order of differential equation. Order of differential equation is 2. Also there are two Li solutions na? Basis is e to the power x and x e to the power x. So a small note, the solution set of a homogeneous differential equation forms a vector space. Solution set of a homogeneous differential equation forms a vector space. Second, if T mapping from V to W is a linear transformation, then additive identity of vector space V is mapped to the additive identity of vector space W. Now let us discuss some examples of linear transformation. T is a mapping from R square to R square, which is defined by Tx comma y is equals to x plus y comma y plus 2. So I am telling a small trick. No need to apply the definition because it will be lengthy. So trick is put x and y as 0 0. If you get 0 comma 0, basically I want to say that if it has additive identity, then it will be linear transformation. Also the map which is defined should be linear, and this is valid only under usual operation. If any different operation is defined, then it will not be valid. So here do by trick, t 0 comma 0, this will be 0 comma 2. We are not getting additive identity, so not a linear transformation. X minus y comma x plus y. Tell me, is this a linear transformation?
Yes, ma'am.
T 0 comma 0 is 0 comma 0, and also it is linear. So this is a linear transformation. Third, is this a linear transformation? बताओ.
It is not because here it is not linear. X square and y square is present. Second degree.
Not linear. That's why not a linear transformation. What about this?
It is also not linear.
Because product of x and y is there. What about this?
This is linear.
Which of the following is a linear transformation from r cube to r square? A part, f x y z is equals to 4x plus y. Tell me.
It is C option, only H.
Reason?
The reason being, third one is cancelled out because it is not linear. And in the A part, Z is not there.
Or you can also say like this, that f000 is equals to 40, not equal to 00. It should be equal to identity, na? Additive identity.
Yes. Okay. But अगर यहाँ पे y होता instead of 4, then it will be linear.
फिर linear हो जाता. Let T mapping from V to W be a linear transformation kernel of T. What was the definition of kernel? Do you remember?
It is a value at which the image becomes 0.
V belongs to domain such that TV is equals to 0 W, means additive identity of codomain. It is contained in V. So first thing is, kernel of T is a subspace of V. Second thing, image of T, or you can say range of T, or RT. It is denoted by RT, range of T. Then it is image of this V vector from this vector space. It is range. Okay. Again, range of this T is a subspace of W. Now next thing is rank nullity theorem. Let T mapping from V to W be a linear transformation where vector space V is finite dimensional vector space. Then rank of T plus nullity of T is equal to dimension of vector space. Rank is denoted like this. Nullity is equals to dimension of V. Dimension of kernel T is known as nullity of T, and dimension of range of T, that RT, is rank of T. Now, do you know what is a linear operator?
No, ma'am.
T is said to be a linear operator on V if T is a mapping from V to V, that is domain and codomain, they are same. Major difference between a linear transformation and a linear operator is that linear transformation is a mapping from a vector space to another vector space, but in linear operator the domain and codomain vector space should be same, and the properties of linear transformation are applied in this linear operator also. Major difference is in this codomain part. Let us discuss some examples. T is a mapping from V to V, means it is a linear operator. TV is equals to 0 for all V belongs to vector space. So this 0 is basically a 0 map, or you can say 0 transformation. So first property was T V1 plus V2 is equals to, apply this linear transformation T on this, it will be 0 na? And the other side was T V1 plus T V2, this will be also 0. So this means T V1 plus V2 is equals to T V1 plus T V2. Other property, T alpha V, this will be again 0, and from other side alpha TV, alpha into 0 is 0. So T alpha V is equals to alpha TV. Both the properties of linear transformation are satisfied. Therefore, T is a linear transformation. Or you can say like this also, T is a linear operator. Means it is also a linear operator and also a linear transformation. But when it will be mentioned linear operator, then the major difference will be in this codomain part. Rest will be same. Now we will find kernel of T. What will be kernel of T here? V belongs to vector space V such that TV is equals to 0. So what will be this? It will be a complete vector space V, na?
Yes, ma'am.
So, and I have told you that dimension of kernel T is nullity, and I am getting kernel of T as V, means nullity is equals to dimension of V. So by this I can find the rank also. Rank of T plus nullity T is equals to dimension of vector space V by rank nullity theorem. Rank of T, nullity is dimension of V only, na? This is nullity. So by this rank of T is 0. So when rank of T is 0, you can see that Rank was range of T na, or I can say image of T. Image T is TV such that V belongs to V, and TV was defined as 0. So this is 0. That's why rank is 0, because rank was dimension of image of T, and dimension of 0 is 0 na. So in this example we have studied about linear transformation, how to find kernel, and how to find range, and by that we have computed rank of T and nullity of T. Next example. T is a mapping from V to V. TV is equals to V for all V belongs to vector space V. So this is a identity transformation, or you can say identity operator. So I have told you two properties to find the linear transformation, to check the linear transformation. TV1 plus V2 is equals to TV1 plus TV2, and T alpha V is equals to alpha TV. Now both these properties can be combined into a single property. T alpha V1 plus beta V2 is equals to alpha TV1 plus beta TV2. You can apply this property also, either this or this. So I will apply this property here, T alpha V1 plus beta V2, and it is defined that TV is equals to V. So this will be alpha V1 plus beta V2. Now V1 will be TV1, V2 will be TV2. So this is a linear transformation. Now let us find kernel of T. V belongs to vector space V such that TV is equals to 0. V belongs to vector space V such that TV is V na. V is equals to 0. When I am taking any vector from this vector space and that vector is 0, then it will be 0 only na, kernel will be 0. Is this clear?
Yes, ma'am.
Next is range of T. And TV is V. So this will be complete vector space V. So rank of T is dimension of V, and nullity of T is dimension of kernel T, and kernel T was 0, so dimension will be 0. You can cross check rank nullity theorem also, no? I'm getting the same result. So now let T mapping from V to W be a linear transformation. V and W are finite dimensional vector space. First, T is 1 1 if and only if nullity of T is 0. Second thing, T is onto if and only if range of T is W and range of T is rank of T is equals to dimension of W. So, in this example only, kernel of T was 0 and means nullity of T was 0 na? Nullity T was 0. This means that T is 1 1 by this result and rank of T was equal to the dimension of the codomain. Rank of T was dimension of V and codomain was V only. So that's why it is onto. And in this example, kernel of T was V. Nullity is not equal to 0. So here T is not 1 1. Rank of T was 0. And this is codomain was vector space V. So here T is not onto na. Is this clear? 1 1 and onto?
Yes, ma'am.
Okay. Next example. T is a mapping from R cube to R cube such that Tx, y, z is equals to x by 2, y by 2, 0. Now T is a linear transformation. We can clearly see by trick. T0, 0, 0 is 0, 0, 0 means it has additive identity and also it is linear. Now task is to find rank of T. Do you want to try this or should I discuss? Tell me. Do you want to try or should I discuss?
Ma'am, you just discussed this one.
Okay. So firstly, dimension of vector space V. Here vector space V is R cube. So this is 3. Now firstly, kernel of T. This is x, y, z belongs to R cube such that T, x, y, z is equals to 0, 0, 0, 0 because codomain was R cube. So by this you can see that x, y, z belongs to R cube such that x is 0 and y is 0. Now my target is to find dimension of kernel T means nullity. Okay. So it will be dimension of R cube minus number of linearly independent conditions. How many LI conditions are there in this kernel T?
2.
So 3 minus 2 is 1. So nullity of T is 1. Nullity of T is not 0 na. So it is not 1 1. By seeing the nullity, you can easily tell whether that transformation is 1 1 or not. Now next is range of T. This is T x, y, z such that x, y, z belongs to R cube. And by rank nullity theorem, you can find rank of T also. Here vector space V is R cube. Nullity of T will be 3 minus, rank of T will be 3 minus nullity of T, 1. So this is 2. This is not equal to the dimension of codomain na, because codomain was R cube. So T is not on 2. Next example. Try this example once. I think now you will be able to do this. You need to find kernel of T, then nullity, and by rank nullity theorem you need to find rank of T, and also check whether T is 1 1 or onto or not.
ऐसे मैट्रिक्स बना के करना पड़ेगा?
नहीं, मैट्रिक्स बनाने की नीड नहीं है.
तो
अभी मैंने सिखाया ही
अगर जो
नहीं.
इसका डोमेन है वो तो डिग्री लेस देन इक्वल टू n का पॉलिनोमियल है. जो इसका रेंज है वो n+1 डिग्री मतलब n+1 डायमेंशन होगी. उसकी जो डोमेन है उसकी डायमेंशन हो जाएगी n+1 और जो
नहीं.
रेंज है उसकी डायमेंशन n+2 हो जाएगी ना, अगर हम पॉलिनोमियल से लें तो.
नहीं, PNR की जो डायमेंशन होती है ना,
हम्म,
वो n+1 होती है, एक ज़्यादा होती है.
हाँ हाँ, तो n+1 की n+2 हो जाएगी.
So we need to find first of all kernel of T.
Yes. So कर्नल ऑफ टी इज 2 0, तो यहाँ पे x जो है पॉलिनोमियल x को 0, तो एक एलआई कंडीशन आएगी x इक्वल टू 0, 1 तो रिप्लेस होगा नहीं.
1 second. tpx this is equal to 0 such that tpx this is p dash x plus 0 to x pt dt is equals to 0. This means that p dash x is equals to 0 to x et dt. Now just think for a second. Only there will be a 0 polynomial which will satisfy this condition. Only 0 polynomial will satisfy this condition. Because I need to take a polynomial whose derivative and then its sum and integration from 0 to x pt dt. It should be 0. This is my target. Only 0 polynomial will satisfy this equation. That's why kernel of t is 0. And when kernel of t is 0, then nullity is 0. Nullity of t is 0 means t is 1 1. Now by rank nullity theorem I can find rank. Rank of t plus nullity of t is equals to dimension of domain PNR. So rank of t will be nullity of t is 0 n plus 1 and nullity of t is not equal to the dimension of codomain. That's why it is not onto. Next example. Try this once. Please mute yourself.
It is neither 1 1 nor onto.
Firstly, check the solution of this. This is a
px equal to c1 plus c2x e to power x.
this one, na?
Yes.
Now kernel of t.
It is not. It is 2 then dimension.
No, I'm telling 1 second. tpx is equals to 0 Px belongs to PNR such that P double dash x minus 2P dash x plus Px equal to 0. Now its solution is e to the power x type. E to the power x and x e to the power x. And domain was set of polynomials, na? But e to the power x is not a polynomial, na?
We can write 1 plus x square plus x cube by 3 x square by 2 factorial x cube by 3 expand कर सकते हैं.
पॉलिनॉमियल हम जब भी लिखते हैं ना तो वैसे वो कुछ इनफाइनाइट तक नहीं जाना चाहिए, कुछ फाइनाइट तक ही रहेगा. हाँ, तो वो पॉलिनॉमियल नहीं है. ओके, तो सो ओनली 0 पॉलिनॉमियल विल सैटिस्फाई दिस.
Okay.
You can understand like this, na? I am talking about dimension. So dimension means number of elements in basis. So basis of a polynomial does not contain e to the power x term, na? Basis of polynomial is like 1x, x square, like this, na? That's why. So nullity will be 0. T is 1, 1. Now, by rank nullity theorem is equals to dimension of domain, means n plus 1. Nullity is 0. Rank is n plus 1. Clearly. Sorry.
No, it is both 1, 1 and on 2.
Because its dimension is equal to the dimension of codomain. So both 1, 1 and on 2. So with the help of rank and nullity, you can easily find whether that transformation is 1, 1 or on 2. Now T is a mapping from V to W. This is a linear transformation. Range of T is TV such that V belongs to vector space B. Now any basis of this vector space is like it contains vectors v1, v2, so on till vn. And I told in the starting only that I will take this as finite dimensional vector space. So that's why I am taking n elements in this basis. So now any vector of this vector space V can be written as the linear combination of these basis elements alpha 1 v1 plus alpha 2 v2, so on till alpha n vn. So if I apply T on both sides, then TV is equals to T alpha 1 v1 plus alpha 2 v2, so on till alpha n vn. So this will become alpha 1 tv1 plus alpha 2 tv2, so on till alpha n tvn. Because T is a linear transformation, na? Now I have done this to tell you that range of T will be tv1, tv2, so on till tvn. Now some more important results. T is a mapping from V to W. This is repeat only. Okay, T is 1, 1 if and only if kernel of T is singleton 0, means nullity of T is 0. So if I draw like this, basically in kernel, if this is V and this is W, T is a mapping from V to W, then identity of this vector space is mapped to the identity of this vector space, and I take a non-zero vector from vector space V and it is mapped to like this. So this is basically the definition of kernel of T. Now this result is important. Let T mapping from V to W be a linear transformation where V and W are finite dimensional vector space such that dimension of V is equals to dimension of W, means dimension of domain is equals to dimension of codomain. Then T is 1 1 if and only if T is onto. T is onto means range of T must be equal to W. Let us discuss its proof also. Proof is very small. T is 1 1 means kernel of T is 0. This means nullity of T is 0. And if nullity of T is 0, then by rank nullity theorem, I can say rank of T is equals to dimension of V. Rank of T, RT is equals to W means range of T is equals to W means rank of T is equals to dimension of W. Dimension of W is equals to rank of T, because by using the given information, dimension of V is equals to dimension of W. Means I have simply substituted dimension of V as dimension of W, because it was given that dimension of V is equals to dimension of W. And what is rank of T? Dimension of RT na? Range of T. This means W is equals to RT because range of T is contained in W. That means that T is onto. And here I have used a small result that if W1 is equals to W2, this implies dimension of W1 is equals to dimension of W2. That's why this was a if and only if statement. And converse is true. One second. Converse will be true if W1 and W2 are finite dimensional vector space such that dimension of W1 is equals to dimension of W2 and W1 is contained in W2 or W2 is contained in W1, and only this will imply that W1 is equals to W2. Okay. One more question. Try this. Find the kernel and nullity and then rank and range also.
Here, dimension of kernel of T is 1. And rank of T, it is also 1.
Nullity is 1.
Yes.
Recheck rank nullity theorem.
Dimension of codomain is 2.
But rank of T plus nullity of T is equals to dimension of domain, na?
Okay, yes, domain. So it is 3. 2 I give.
So kernel of T is
Achha.
nullity of T is dimension of R cube minus number of Li conditions. There are 2 Li conditions. 3 minus 2, 1.
1.
So as nullity of T is 1, so it is not 1, 1. And by rank nullity theorem, rank of T will be 2. And it is equal to dimension of R square codomain. So it is on 2. Now try one question. Let T mapping from R cube to R cube be defined by T x1 x2 x3 x1 minus x2 x1 minus x2 comma 0. So here also you need to find nullity and range.
These both are x1 minus x2, x1 minus x2.
Both are x1 minus x2. This is MCQ only. Only one option will be correct.
It's A option.
x1 minus x2 x1 minus x2 means x1 minus x2 is 0 means there is only one Li condition, na? So nullity will be 3 minus 1, 2. So A part is correct. Let us check remaining options also. Range of T. So rank nullity theorem, rank of T plus nullity of T is equals to 3. Rank of T is 1, na? And it was saying that dimension of range of T is 2. This is wrong. Range of T is not equal to nullity of T. Nullity of T is not contained in range of T. So answer is option A. So here you need to find dimension of range space of T. Find it.
It is 1.
No. What was your approach?
I took it as r square because sy is there, na? So I have taken r square. So if I map t r square to r square, then the then it is 0. I have taken fx as 1 continuous function है, continuous real
One
valued
second. You
function. So
cannot take
t
this.
of 1
One
is
second.
sine of x plus y.
एक मिनट सुनो. You cannot take this as r square. This is C01.
Continuous function.
There will be infinitely many continuous functions, so its dimension is infinite. You cannot apply here rank nullity theorem or like this. Here approach will be different. You need to see that how many elements will be there in the basis of this range space. So what can we do here? T fx is equals to 0 to 1 sin x cos y. Open the identity of sin a plus b.
Hmm.
So you can take sin x outside 0 to 1 cos y fy dy plus cos x 0 to 1 sin y fy dy. Now no need to find this value. You cannot find, as this is a numerical answer type question, you need to write a final answer. So you cannot take any fy. I mean अगर MCQ होता तो आप कुछ हिट एंड ट्रायल से लेके कर सकते थे fy को, चाहे 1 ही ले लेते. But here you cannot take fy, any value of fy. So you can simply write sin x into a. You can take this, whatever value will be there, you can take this as a constant. So tfx is equals to this, and x was from 0 to 1. Now you can see this is tfx, na? This is range space only. One second. Range space is this, na? tfx, such that fx belongs to these continuous functions. Means a sin x plus b cos x. X belongs to 0 comma 1. You can say like this, that range space of t is spanned by sin x and cos x, na? They are li also. Li also, spanning is also done, because I am able to write this as a linear combination. So basis of range space of t will be
2.
Dimension will be 2. So the main thing was that this, its dimension is infinity. So I cannot apply rank nullity theorem here. So I simply check the image of this fx. Okay. let Rx denotes the vector space of all real polynomials let D mapping from Rx to Rx denote the map derivative of f for all f. Then A part D is 1 1, B part D is onto, C part there exists E mapping from Rx to Rx so that D part there exists E mapping from Rx to Rx
In this case, it is not 1 1.
Reason?
Reason being, if we take the derivative equal to 0, then it will be 0 for the constant function also. So there would be a single element also in the null space of dimension of kernel. There could be constant value, so it will not be 0 element. So it is not 1 1. And so dimension, it is not onto also, because if there would be a single element, say Rx to Rx map is same. Dimension is same, domain and codomain. So it is not onto also.
Here you are saying that there will be constant polynomials, na?
Yes, constant polynomial. and T of EF.
D is not 1
Yes.
and after that for onto
Not onto because there is a dimension, no? Because the domain and codomain dimension is same. So if there is a dimension in kernel, then the range space rank will not have the same same dimension as codomain.
but what is the dimension of this Rx? I mean, dimension of Rx is infinite now.
Hmm.
So
So
here
we
also you
can't
cannot apply
we
rank
can't
nullity theorem.
so we can't find rank here. No?
So rank can be computed by using range only.
Yes.
Or you can apply the basic definition of onto which we used to use in class 12th.
Yes, that is the range is equal to codomain.
For all
Hmm.
fx. So fx is
Hmm.
a polynomial and it belongs to Rx. So I can take like this. Then there exists gx equal to a naught plus it is the map is derivative na. So
Hmm.
here I will take integration of this fx. Then only derivative of fx will be derivative of
Hmm.
gx will be fx. So a naught
Hmm.
x plus a1 x square by 2 plus a2 x cube by 3 and so on,
Hmm.
such that derivative of gx is equals to fx. So D is on to.
Hmm.
So option B is correct. Now in option C it is saying that there exists E belongs to Rx such that derivative I mean DEF is equals to F. Let us check this also. Now it is saying in C part there exists E mapping to from Rx to Rx so that for all F. Now you need to think of a EF such that when this derivative map is applied to it, then I will get F again. This is simple na?
Hmm.
If I have EF as some integration map, I mean some integration
Hmm.
and I will apply derivative on it, then I will get that simple fx only.
Yes. Similar to the earlier example, the taken for the onto function.
0 to x fx dx. This will be fx. So option C is correct. Now in option D it is saying that there exists E mapping from Rx to Rx so that for all F.
Hmm.
So means there is some mapping which is applied to this derivative map and then I get F again.
Hmm.
If I take fx as 1,
Hmm.
then derivative of f is
0.
0. And if I use this same map, this one,
Hmm.
so derivative 1 because it is saying like this na E df f is 1
Hmm.
E 0 and it should be equal to this integration map 0 to x 1 dx, but it is coming to be it was
X.
0D
It's a
is
0 D.
0.
0.
But it should be equal to f, and f was
1.
1. So by
1.
taking an example, I have discarded this option.
Mm.
So option D is wrong. So answers are option B and C.
Mm.
Okay. Now let us move to the next concept. Let T mapping from V to W be a linear transformation and V, W be finite dimensional vector space. Dimension of vector space V is greater than dimension of vector space W. If this is the case, then T cannot be 1, 1. And if dimension of V is less than dimension of W, then T cannot be onto. For example, T is a mapping from R cube to R4, B linear transformation, and T is onto. Now I need to find cardinality of S. Cardinality of this set, which consists of linear transformations mapping from R cube to R4 and T is onto. Now use this result. Dimension of R cube, dimension of V, it is 4. Dimension of V is less than dimension of W, means T cannot be onto, and this set consists of T is onto. So cardinality of S will be empty, na? Is this clear?
Yes, ma'am.
Okay. And also if you want to verify by rank nullity theorem, it is given that T is onto. So whenever T is onto, then rank of T means dimension of RT is equals to dimension of R4, which means 4. Okay. So rank nullity theorem, rank T plus nullity of T is equals to dimension of domain 3, and rank of T is 4. So rank of T is -1, which is a contradiction. Rank cannot be negative, na? Oh, sorry, nullity cannot be negative, na? I mean dimension cannot be negative. So that's why I'm getting a contradiction. There are two ways to do this question. So by this also, cardinality of this set will be empty. Similar example. Here V is R4, W is R cube, dimension of V is 4, dimension of W is 3, so T is not 1, 1, but whenever dimension of domain is greater than dimension of codomain, then it is onto. So cardinality of S is empty. Okay. Or you can do with another rank nullity theorem also. T is 1 means nullity is 0. Now by rank nullity theorem, rank of T is 4. You can see that rank of T can be at most 3. It cannot be greater than 3, na? It cannot be greater than the dimension of codomain. Is this clear?
Yes, ma'am.
So that's why cardinality of S is empty, because this is a contradiction.